we have a puzzle made out of some gears. The bottom gear has a diameter of 4.25 inches. Then there are a couple of other gears, one with a diameter of 3.5 inches, then one with a diameter of 2.75 inches, and then the smallest gear that moves has a diameter of 2 inches. If I spin the gears, I could measure their speed in revolutions per second. So for example, if I was spinning them so that they were going around 15 times per 10 seconds, their RPS, or revolutions per second, would be 1.5. 15 revolutions per 10 seconds, 1.5 revolutions per 1 second. The linear speed is how fast a point on one of the gears is moving as it spins around. And that is measured in length. So the length of the circumference is what guides that per unit of time. So for example, let's suppose I was spinning them at 15 times per 10 seconds, or 1.5 revolutions per second. If we work with the smallest gear that moves, the 2-inch gear, its circumference is 2 inches times pi times diameter, or approximately 6.28 inches. I'm spinning it 1.5 revolutions per second. That means that it's making 1.5 circumferences every second. So 1.5 times the circumference is how many inches it's moving per second. That is its linear speed. Linear speed means length per time, whether you're a car going on a straight road, or a person running around a track, or a point going around on a gear. It's what length are you moving per unit of time. Now for the bigger gear, it had a diameter of 4.25 inches. If I were spinning it at the same revolution rate, okay, so 1.5 revolutions per second, the circumference is bigger because the diameter was bigger. So the circumference was approximately 13.35 inches. So, oops, I have inches per second, but that's just the circumference, so it's just inches. So again, that was the diameter times pi. So 1.5 circumferences are being traced per second. So 1.5 times the circumference is how many inches per second it's moving. So it's moving 20.03 inches per second. So a point on the outer gear is moving at a speed of 20.03 inches per second. Now keep in mind that linear speed means length per time, and you could report it in all kinds of units. I just reported it in the most straightforward because we were told inches for circumference and we were told revolutions per second. So that led kind of immediately to inches per second. But we could convert these same speeds to miles per hour. And for example, for the 2-inch gear, if the 2-inch gear is moving at 1.5 revolutions per second, that is a linear speed of 9.45 inches per second. There are 3,600 seconds in an hour. So notice if I multiply by the ratio 3,600 seconds per hour, the seconds cancel out. There are 12 inches in 1 foot. And so if I multiply by the proportion 1 foot per 12 inches, the inches cancel out. And then if I multiply by the proportion 1 mile per 5,280 feet, the feet cancel out. I'm multiplying these fractions together, and notice the units told me the correct form to multiply the fractions because I wanted to cancel out inches, I wanted to cancel out seconds, I wanted to cancel out feet to get miles as the numerator unit and hours as the denominator unit. So when you multiply fractions, you multiply straight across. And if I multiply 9.45 times 3,600 times 1 times 1, I get 34,020, and that's miles. And then if I multiply 1 times 12 times 5,280, I get 63,360 hours. If I then divide 34,020 miles by 63,360 hours, I get approximately 0.536 miles per hour. So not very fast. If we did the same unit conversion for the larger gear that was going 20.03 inches per second, and I converted seconds to hours and feet to inches to feet and then feet to miles, I get a speed of 1.138 miles per hour. Again, linear speed is linear speed. It just means a length over a unit of time. So I could also measure in the scientific units of centimeters or kilometers. The 2-inch gear, that means the diameter was 2 inches. I could also report that as 5.08 centimeters, and the circumference would be pi times 5.08 centimeters. I still am going to do the same process. It's going around 1.5 times per second. So 1.5 times the diameter gives me the inches per second, or sorry, centimeters per second, not inches anymore. And if I wanted to convert to kilometers per hour, there are still 3,600 seconds in an hour. Then there are 100 centimeters in 1 meter. There are 1,000 meters in 1 kilometer. And so notice the centimeters cancel out, and the seconds cancel out, and the meters cancel out, leaving me with kilometers per hour. If I multiply 5.08 pi times 1.5 times 3,600 times 1, I get 86,180.2 kilometers. Then in the denominator, 1 times 100 times 1,000 is 100,000 hours. And then you can reduce that to 0.862 kilometers per hour. So units can be any units as long as your numerator is a length and your denominator is a time, and it's accurate for the circle and the amount of time you're talking about. We have a salad spinner with a diameter of 8.5 inches, and we've placed a bright blue A on it, so we can count how many times the A goes around to figure out the revolutions per second of the salad spinner. So we're going to pump it up and let it go, and we'll track that A, and we'll find out how fast a point on the salad spinner is spinning. Our salad spinner had a diameter of 8.5 inches, and we attached that bright blue A on it so that when we filmed it spinning, we could watch for the A and count how many revolutions it made. If you slow down that video, it was actually a 9-second video, so in real life 9 seconds went by. If you slow down the video, you're able to count that the salad spinner went around 60 times, so it made 60 revolutions in 9 seconds. So its revolutions per second was 6.67 approximately, the 60 revolutions divided by 9 seconds. If the diameter is 8.5 inches, then the circumference is pi times the diameter, or approximately 26.7 inches. So every 9 seconds, it was going around 60 times. So 60 times the circumference is how far a point, say that A, went around in 9 seconds. If we multiply the 60 by 26.7, we get 1,602. That's how many inches per 9 seconds. And if you reduce that, you get a linear speed of 178 inches per second. So that is its linear speed in inches per second, But we might want to interpret that in terms of miles per hour because we're a little bit used to understanding how fast something is really going if it's in miles per hour. So I'm going to take my 178 inches per second, and that's per 1 second. There are 12 inches in 1 foot, and there are 5,280 feet in 1 mile. So notice now I have miles in the numerator as my unit. That's the unit I'm striving for. And there are 3,600 seconds in 1 hour. And notice I now have hours in the denominator. That's the unit of time I'm striving for. So the unit of inches divides out the unit of inches. The unit of feet divides out the unit of feet. The unit of seconds divides out the unit of seconds. And I now have all of my fractions that I can multiply together, leaving me with miles per hour. So if we multiply together 178 times 1 times 1 times 3,600, we get 640,800, and that is miles, but that's not how many miles per hour. If we then multiply 1 times 12 times 5,280 times 1, we get 63,360 hours. So if you reduce that fraction, then we get a speed of 10.11 miles per hour. So a very fast running pace, a reasonable bike riding pace. That's how fast a point on the rim of the salad spinner was going. Another fun example of linear speed is to think about how fast a point on the surface of the Earth is moving at any point in time. Suppose we're on the equator, which is that great circle around the center of the Earth, and the Earth spins around once per 24 hours. So putting all of that information together, if we are on the equator and we then have a radius of approximately 3,960 miles, giving us a circumference of approximately 24,881 miles, we're spinning once per 24 hours, so we're going around 24,881 miles per 24 hours. That reduces to a little more than 1,000 miles per hour, 1,036.7 miles per hour. So we're going pretty fast. If you're north or south of the equator, you're not going quite as fast because your circle is smaller, but still we're all moving pretty fast, so we can all scream like Liesel in The Sound of Music.